Okay, thanks, Mark. So, yes, I'm sure many of you may know already, but in case you don't, this summer there will be the Amplitudes Conference and the Amplitudes School, which we held on an annual basis these days. The Amplitudes Conference is in Queen Mary, 29th June to the 3rd of July, and the school will be the week after, so 6th of July to the 10th of July, and that will be in Southampton, organised by Omar, principally, I have to be honest, and with some small assistance from myself. And what do I want to say? Oh, I just want to encourage you to think of contacting your PhD students or postdocs, also welcome. We are slowly filling our places. We have a number of places for accommodation available, but that number will run out eventually. So we are serving up accommodation on a first-come, first-served basis, essentially. So please just encourage anybody who might be interested to sign up for the school to do so in good time. You have another comment? Okay, yeah, thank you. That's true. And there has been a general email circulated. Some of you may have seen it, that might have come your way. And there are more details on there, including lecturers. Okay, brilliant. I don't think I have anything more to add to that. Just to encourage you to please apply or contact junior colleagues to apply. Okay. Now I have to switch here. Okay, good. All right. So what am I going to do today? So I would like to tell you about some work that's clearly related to scattering amplitudes, but it's actually a kind of a generalization of one of the realizations of scattering amplitudes in n equals 4 super-Yang wheels, which is via light-like Wilson loop operators. And I'm going to take a step away from amplitudes and just study light-like Wilson loop operators in their own right and think about correlation functions of multiple such loop operators. And the main reason I'm interested in doing that is, well, there's several reasons why it's interesting to do, but for the context of this workshop and this program, it's an extremely natural generalization in which much of the same geometry that shows up in the original Wilson loop amplitude problem also applies, but there's some interesting new features which I hope I'm going to highlight as we go through this talk. Okay, this is work in progress, so I've given talks on this a few times before. The main difference now is we actually have some papers that you can read about this. This is based on work from the group in Southampton. There's a paper in December with Omar and two students, Matthew Rochford and Rowan Wright, and two subsequent papers that came out relatively recently, also with students in Southampton. Plus some more work in progress. I hope I'm going to come to BCFW recursion relations in this talk. I'm promising you there will be some paper relatively soon also on BCFW recursion. Okay. So here's a cartoon of diagrams that are likely to show up in this talk. So let me begin from the solid ground where there's a sort of a well-studied story from many people, including many people in this audience. We study scattering amplitudes in maximally supersymmetric Yang-Mills theory in the planar limit. Okay? And one of the main reasons we do this is that it reveals lots and lots of interesting structure, perhaps more than you might necessarily have thought, even for a maximally supersymmetric Rig gauge theory and even in the planar limit. One of the unexpected features is that you can relate a scattering amplitude with null on-shell external momenta, saying pi squared equals 0, and momentum conservation. Just by a simple change of variables, you dualize the momenta and write them as a difference of new dual variables. That solves this momentum conservation condition. And you can rewrite the space of momenta by putting them end to end in some new X space. And you get this piecewise light-like closed contour. And what's remarkable, so that's just a statement of kinematics. It's natural because we're in the planar limit, and so I can take a color ordering, specified cyclic ordering of the external momenta. So that tells you what's the natural set of dual coordinates to introduce. And what is surprising is that there's actually another object in the same theory that you can compute with this given data, which is the Wilson loop, which is the vacuum expectation value of the trace of the path-ordered exponential of the connection, the gauge connection, around this contour. A different object, but kinematically it has the same dependence just through this change of variables, and remarkably, you get the same functions coming out. This has some understanding in the context of string theory. So in string theory, you can derive a duality between maximally symmetric gauge theory in Minkowski space and a certain supersymmetric string theory in anti-de Sitter space across the sphere. And in that context, you can set up a scattering of open strings that would correspond to gluons. They get stuck to some surface in ADS. In the strong coupling limit, which is like the classical limit for string theory, they're meant to sweep out some world sheet. And under this change of variables, which in the string context gets encoded by a transformation called T-duality, you get a different minimal surface, but one which ends on this piecewise light-like contour on the boundary of ADS and sweeps out some surface inside the interior. And then you're meant to compute the area of that surface. So this transformation between something that looks like a scattering amplitude and something that looks like a minimal surface, it comes from this T-duality prescription. And this minimal surface is, according to the ADS CFT correspondence, the way you would compute a Wilson loop in the gauge theory at strong coupling. So at strong coupling, string theory does give you some justification for this. Perhaps what's more surprising is that it seems to also be true by computation at weak coupling. And then there were further arguments based on why you might expect this to hold at any value of the coupling, again from string theory, but in the planar limit only. Okay, so this is by now a very, very well studied duality, and I'm not expecting you to register all of these authors and all of these references, but there are sort of so many subtopics in this field with many, many people who've studied them. From the original string theory T-duality arguments that I was talking about, the fact that you get new symmetries through the fact that the amplitude, the symmetries of the Wilson loop are not obviously the same symmetries of the amplitude, and therefore you get both sets of symmetries, including the conformal symmetry of the Wilson loop, which we call dual conformal symmetry. Some direct computations, and perhaps of most relevance here, has led to this general understanding of being able to compute in this theory from some geometric perspective, and it's led to the introduction of the amplituhedron as a method for computing, if you like, a geometric formulation of the integrand at L loop order for the scattering amplitude, or Wilson loop. Okay, now, one of the things I want to highlight is, because we have a duality, some of the properties that show up in the study of these things are sort of more naturally associated to the amplitude way of looking at things, and others are more naturally associated to the Wilson loop way of looking at things. I would actually characterize the amplituhedron. Okay, the amplituhedron is a very geometric object, but it feels more naturally, actually, sitting on, despite the name, sits more on the Wilson loop side of this duality. And the reason I say that is it was formulated connected to the twistor space that's actually associated to this dual space, these x's. So it's naturally associated to the dual space description and the light-like geometry that's in there. There's other versions of the amplitude-hedron. There's the momentum amplitude-hedron, which sort of feels perhaps more closely related to the amplitude side of the correspondence. So if you want to know about the momentum amplitude-hedron, you should ask the authors who are sitting at the back here, Tomek and Livia, also Matteo. Thank you. Okay, so there are two things that show up. So if you've got something that shows up on one side, there should be a corresponding way of understanding the same thing on the other side. It may not immediately be obvious. So one thing that I would point out that has been understood this way and isn't immediately obvious is, from the amplitude perspective, we have BCFW recursion relations. And in the amplitude context, we can understand that very nicely by thinking of the pole structure of scattering amplitudes, deforming them in such a way that preserves momentum conservation, and then exploring the analytic structure of the deformed object to feel out some of those poles. And when you understand the poles, you can then reconstruct the full answer because you have enough analytic information. This very amplitude-y way of thinking about BCFW recursion relation. That's the context that it was first formulated. However, there is another way of thinking about BCFW recursion relation, which sits on the Wilson loop side, and that goes under the name of holomorphic linking, and it was studied in a paper of Bullimore and Skinner. And we're going to come back to that and hopefully use that to understand an analog of the BCFW recursion relation for something that's not an amplitude, but a correlator of multiple light-like Wilson loops. Okay. All right. Enough to say on that. Okay, so we are going to try and extend the right-hand side of the duality. It's not going to be a duality anymore. We're just going to study these objects that are correlators of multiple loop operators. So it's not dual to a scattering amplitude, at least not directly. On the other hand, there are physical reasons why this should be an interesting thing to think about. So if I study, for example, if I consider the correlation function of two loop operators, and I go to the large n limit, I should be studying Feynman diagrams that now, instead of having a disk topology that was specified by one single loop, they now have a cylinder topology or an annulus topology that span between two loops in the large n limit. And at strong coupling, you might expect, although I don't know, but you might expect there should be some minimal surface picture where the minimal surface of the string actually has this cylinder topology, specified by two loop boundaries, and then it has a cylinder topology inside ADS. The main thing that I want to emphasize here is that there are several techniques which we can apply to the single Wilson loop case, which we can extend to this case. And so these things become surprisingly computable, despite looking like quite complicated objects. So one piece of technology that's very useful is to try and understand Wilson loops in the twistor language. So there's a nice formulation of this due to Mason and Skinner, which allows you to understand Wilson loops and allows you to supersymmetrize them in order to match, for a single Wilson loop, the MHV expansion of scattering amplitudes. I will hopefully describe the BCFW recursion and relate this to this linking, holomorphic linking description. It kind of relies on this twistorial description of the Wilson loop to derive and argue for. There is a differential or a differential integral equation that these Wilson loops obey, called the Q-bar equation, which comes from the fact that we have supersymmetry in our theory, but half of it's not manifestly realized. So it's realized in a slightly complicated way. The half that is realized in that way is called Q-bar. And you get an interesting and quite powerful equation which relates different orders in the coupling expansion. So if you understand enough about tree level, you can derive something about one loop by using this differential equation. Conversely, if you understand enough about one loop, you can keep going. You can just derive something about two loops and so on in higher orders. And hopefully also I'll have a chance to sketch that something Paul briefly mentioned in his talk, that you can relate Wilson loops to certain limits of correlation functions of local operators. And you can also consider different limits of the same correlation functions of local operators, and you can relate these to these correlators of multiple light-like loops. Okay, so some basic starters on Wilson loops and how you compute them. And this is ancient technology now. So what do? You take a contour. For us, it's this piecewise light-like contour. You have a gauge field, a one-form gauge field, gauge connection. You take its path order, so integrate it around the contour, and you take the exponentiation of this, and then you path order, which just means for each integration, you go up to the last one and stop there. And then once you've gone all the way around in a loop, you take the trace, and this gives you a gauge invariant, non-local operator in the theory, because it's defined on this whole contour. Okay, and then the Wilson loop, where you compute the vacuum expectation value of this loop operator. Okay, so in practical terms, what do? So we expand out this exponential. Okay, I take the first term is just 1. I normalize appropriately so that the first term is 1. Then I have a term that's linear in the gauge connection. And I haven't written it down here because now I have to compute the vacuum expectation value, and I've got nothing to saturate against a single power of the gauge field. So when I compute the vacuum expectation value, there's nothing left. Or equivalently, even classically, if I'm in SUN, I get a single trace over one of the gauge generators. And it's even 0 classically for SUN. So there's nothing at linear order. Then you go to quadratic order, and you get 2 insertions of the gauge field, A. Okay, and you integrate these. So these are at some points x1 and x2 that lie on the contour, parameterized by points t1 and t2 that take you all the way around. You integrate t1 less than t2, that's the path ordering. And this is the path ordered exponential. Here's the vacuum expectation value. You have some color factor to do with the trace of the gauge generators. And now I'll compute this vacuum expectation value. I should contract these two fields with the propagator, which takes this form, and I've written it in dimensional regularization to shift the power by some epsilon. Okay, but in 4 dimensions, it's just x squared, the difference of squared. And there's some saturation of the gauge group indices and the space-time indices. And now I have to integrate that over T1 and T2. So you're getting diagrams that look like this. 2 insertions of the field, a propagator, which is this object, between them, and then I have to integrate them around the loop. And because the loop has got various segments, there are different types of diagram that can arise. I can begin and end on the same edge, but that actually vanishes because the edge is light-like. I can begin on one edge and go to the next edge, and then you find this integral diverges in 4 dimensions, so it's regulated by this epsilon. You get poles in epsilon for such a diagram. Or you can go from one edge to a distant edge, and this you find is finite in 4 dimensions, and you can set epsilon to 0 when you evaluate this diagram, as long as you're truncating it at the finite piece. All right, so there's the result for the divergent diagram. You find that, in fact, it has a double pole in epsilon. Here is the result for the finite diagram. It's just a 2-fold integral, so it's no surprise it comes out in terms of dilogues. And I've written some explicit version of it. Don't need to digest this formula, just know that it's simple enough you can write down explicitly. I'm just going to call this finite diagram Ij, to go from this edge to this edge. Okay, and then you add up all the diagrams, so you get a bunch of divergences associated to each corner, and you get a finite term, which is the sum over the other finite diagrams. And this theory has a conformal symmetry. The conformal symmetry plays nicely with the contour, so a conformal transformation of a light-like contour is another light-like contour. So that's an important feature of these particular loops. So therefore, we just need to conformally transform the points that define the corners, and we get the new object. And we should expect this thing to be at least formally invariant, except for the fact that there were divergences, and the divergences can lead to anomalies in the transformation. So in fact, what happens is you find when you add up this finite piece, you've got the divergences, and then the finite pieces are somehow missing some of the diagrams, and you find it's not conformally invariant, but instead its variation is not quite zero, but its non-zero variation is localized at the corners. And it has this particular form. You take 2xi minus its neighbors, and then the log of the only distance that you can form across the corner I. So this anomalous conformal Ward identity. Okay. And in fact, the general structure for a single Wilson loop looks like this. So we get, as we now thinking about all orders in perturbation theory, not just truncating at the quadratic order when I expanded, okay, and not just including diagrams that are single propagators, but also vertices that you get from the Yang-Mills action. You should find a structure that looks like this, at least in the large n limit. You find that there are factors that are divergent that encode the divergences associated to each corner, and they factorize over the corners. You find a factor that includes this anomalous conformal transformation that I just showed you on the last transparency. It's literally the same function that I just showed you that you got at quadratic order. The only difference is that you multiply by an object that we've seen before, at least certainly I think in Jake's talk we certainly saw the cusp anomalous dimension. It's a function of the coupling in this of the gauge theory, so it goes to all loop orders, but it factorizes from this once and for all determined quadratic order function, which was just the bunch of dialogues that we had. Okay, so this is the anomalous conformal piece. And then there's the heart of the beast, right, which is this conformally invariant factor, which is finite. You can set epsilon to 0, so you can compute this in 4 dimensions in principle, and it's conformally invariant, but a priori we know nothing else about it. This now one has to determine order by some tricky computations, or as we heard in the previous talk from Omar, you notice some interesting analytic structure that this thing contains, and then maybe you take that as an assumption and you make use of that in order to perform a bootstrap, maybe making an ansatz over polylogs, over cluster variables in the alphabet, and so on. Okay. All right, so that's the basic structure of a single Wilson loop, and now I want to tell you that the same structure pertains to the correlator of multiple loop operators. So now I'm just going to take many such contours, okay, and I'm going to say, well, I've used the variable m here, so apologies to amplituhedron people who like to study the amplituhedron. This is not the amplituhedron m, so this is just the number of loop operators. M equals 4 in the amplituhedron sense here always. Okay, so I'm going to have a correlation function now of operators, many such operators defined on multiple such contours. And the divergent structure should be the same. So you factorize over corners and you factorize over individual operators. So it's just a product over all the loops. For each loop, a product over all the corners, and that gives you the divergence. There should be an anomalous conformal transformation which factors over all the loops, and that's the same function that you get up here. And this is the same function that you get up here. And then what's left over is a finite conformally invariant function that now depends on all of the data of all of the loops and generalizes the case for m equals 1. Okay, right, so now some comments on color structure. So we have an SUN gauge theory, and we're often thinking of taking the large n limit. So one contribution, so let's imagine the correlator of 2 loop operators, n1 points and n2 points, 2 different loops. One contribution that you get is just all the diagrams that sit entirely within one loop and diagrams that sit entirely within the other loop, and nothing goes between them. So that just gives you the product of the two individual loop operators. That's certainly one contribution that you get to this object. And then we just define all the rest to be the so-called connected part. And this is the interesting new piece that you get. One thing to bear in mind is that this new piece will be suppressed in the large n limit with respect to the factored piece. So this will be 1 power of 1 over n squared down from the leading term. And this factored structure with the divergences and anomalous conformal piece just factors through this. So I can write the same equation also for the finite remainders. And similarly, if you wanted to do 3 loops, there's a piece that's completely factored, a piece that factors into 1 loop and the connected part of the other 2 in the 3 combinations, and finally the new piece for 3 loops is fully connected. These have a hierarchy in powers of n counting. Okay, so let's do a calculation. Let's compute the simplest contribution you can think of to the connected part of 2 loops. And that's just do the same diagrams that we had before. We just send a propagator. We expand each of them out to linear order, and we send a propagator across, and we integrate this end round this loop and this end round that loop. Okay, there will be some color factor as before, and if I'm in SUN, because I get single traces here, this actually vanishes. Okay, but if I'm working in UN, in particular if I'm working in U1, it does not. We can compute it and just look at its structure. So what do you get? You just sum over all the edges I, all the edges j, that same function, because the function was just defined as an integral over 2 like edges that had nothing to do with each other. It's the same combination of dialogues that we had before. It's just that I lies on one loop and j lies on the other, interpreting the labels differently. Okay, so this time you add everything up. There's no gaps. You get a very nice finite and conformally invariant function this time. So we can write it out manifestly as functions of cross ratios, conformal cross ratios. And here I've given one such expression. So there's some dialogues, and in this expression there's also some log-log terms. The V's are cross ratios that you define like this, conformally invariant quantities. And there are more than you need, so they satisfy certain product relations. You can just, by going around the loops, you can verify. If you take the product over labels on one loop, you get 1. Okay, but that's a way of computing the first non-trivial and completely explicit conformally finite remainder for 2 Wilson loops. Very simple answer, just weight 2 dialogues and logs. Okay, and in fact, that computation also gives us the same, the first non-trivial answer for the SUN theory. I said in the previous computation it vanished in SUN, but for SUN, the leading contribution, I have to have at least 2 insertions on each loop in order to get a non-vanishing result. And now, because there's only 2, there's no ordering of these points as I go around. No one is before the other because there's only 2 of them. Same here. And so, in fact, this thing factorizes. You simply integrate both points over everywhere. So you can write this thing as a product of the same function that we just had in the abelian case squared, because we get 2 propagators. So that's that dialogues and log-logs all squared, and the first contribution. So each dot really comes with the power of the coupling. It's g to the 4, and some color factor that in SUN takes this form. And if I wanted to do 3 loops, this would be my first non-trivial diagram, and I'd get a product of the 3 abelian results over the 3 pairs of loops. Okay, so doing the abelian theory is a good thing, because it also gives you the first non-trivial terms for SUN. Okay, now, as we've seen before in a number of talks, I think, this light-like geometry can be very conveniently parameterized using twistor variables. These variables are called momentum twistors. So what you do is, a way to describe this is, if you look at the difference between two neighboring points, these dual points, it has to be null. So these 2 points are like separated. And if I represent them in this 2 by 2 matrix notation or bispinner notation, it means that the length of this is actually the determinant of this matrix. So it actually factors into an outer product of two component vectors. Okay, and then you can form this other object. This is called the incidence relation. You pick your x, contract it with this lambda, and you get another object mu. And this pair, lambda and mu, is the momentum twistor variables. 4-component object, but it's also homogeneous in lambda and mu. So you mod out by a scaling, so it actually lives in projective 3 space. Okay, and then I can represent the geometry that we had before by dots. These points live in P3. The lines are defined by 2 pairs of adjacent dots. The lines correspond to the xi's in space-time. 2 xi's are null separated if the corresponding lines intersect in P3. So to specify the geometry, you just need to specify the intersection points. And if I have 2 such contours, I just describe two sets of points. Okay. So there's actually a way of formulating the Wilson loop computation directly in this twistor space, instead of referring back to the space-time computation. And it provides a way to supersymmetrically extend the model to include Wilson loops that have some Grassmann sectors that correspond to the different helicity sectors of the scattering amplitude when you're doing a single Wilson loop scattering amplitude duality. Okay, so the way that you do that is you work on super twistor space. So P3 becomes P3/4. There's some extra Grassmann variables that I've called chi here that go along with the z's that we had before. Combine these into a curly z super twistor. And the main heart of the thing is that actually now you're in a 3-dimensional space, albeit complex, so you can consider a Chern-Simons-like theory in this space. Okay, so you write down the Chern-Simons 3 form, okay, and here everything happens in the anti-holomorphic half. So these are 0,1 forms, that's a D bar, another 0,1 form. This is the Chern-Simons form. So this part of the theory is meant to describe self-dual Yang-Mills. And now, if we want to include the full Yang-Mills, we should do an expansion around self-dual Yang-Mills to include the non-self-dual part of the theory. And in this formulation, that has a funny non-local looking description. So you have to integrate over lines. The interactions take place on lines in twistor space rather than at points. But that's okay. In some sense, it's natural because lines in twistor space are points in space-time. So the interactions are still local in space-time. And what you do is you pick a line, corresponds to a P1 inside P3. You take your D-bar operator, covariant D-bar operator, pull it back to this P1, and then you compute the log det of this D-bar operator. And you integrate over the space of lines. It's meant to be a funny, non-local, infinite expansion in interaction terms. And it's meant to complete the Chern-Simons theory, or the self-dual theory, to the full theory. The coupling strength, you mean? What do you mean, sorry? Yes, I've omitted a prefactor which includes the coupling constant. Sorry, it's more of a cartoon of the formula than the actual formula, sorry. Okay. All right, so you've got this theory. Now you need to formulate the object that you want to compute. So this you do by defining a holomorphic frame. So you take some curve. Well, we know what our curve is. It's this sequence of intersecting lines. The line's really a P1. So it's a sequence of intersecting lines inside P3. And then what you want to do, suppose we have a segment of it for the time being, is you want to find a rotation frame. So there's an SUN connection. You want to find an SUN transformation that rotates your d bar plus a, your covariant d bar, just back to the flat d bar operator. So you find some holomorphic function h that does this operation. Okay, and if you can do that, then you can define this kind of parallel transport operator, completely analogous to the case of an ordinary Wilson loop in space-time. So you find a U that obeys this equation. It's annihilated by d bar plus a, and you look for it to have the boundary condition such that when the 2 points coincide, you get the identity. You're just solving this differential equation. Okay, and you can solve it in terms of finding this holomorphic frame. So it's h at z, inverse of h at z bar. That obeys the equation and the boundary condition. Okay, and it also obeys the usual concatenation rule for parallel transport. If I go from z to z prime, then I go from z prime to z double prime. That's the same as z to z double prime. Okay, so now we're going to build our curve out of these components, these intersecting lines. We've got several lines that intersect at certain points. Okay, so each line is parameterized by some s. So the point on the line, which is called zxi of s, is just s times zi minus 1 plus zi. So that on the parameterization, s equals 0 corresponds to the point zi, and s equals infinity corresponds to the point zi minus 1. Okay, and now our loop operator, what do? It's literally exactly the same formula. Trace of the path-ordered exponential of the integral of the gauge field, something holomorphic, everything anti-holomorphic here, around our loop. Technically, what do? I pick a base point, I parallel transport to 1, then to 2, then to 3. I go all the way around to n, back to the base point, take the trace, and then you get something gauge invariant. And because of the trace, it's also independent of z. Okay, it was completely analogous to the definition of the Wilson loop that I gave you before in space-time. So what do? To compute it, we do the same thing. We start expanding our path-ordered exponential. It starts with 1. We have a linear term. We have a quadratic term. In this language now, the ordering comes by these poles. You can sort of read off that you started at 0, and you go to s prime, and then from s prime you go to s double prime. And if I went to the next term, there'd be s double prime to s triple prime, and so on. Okay, and now to compute, we need to build propagators, and also to fix the gauge. And a commonly chosen gauge fixing is an axial gauge. So there's some reference point called z star, some reference twistor. Okay, so the formalism has some reference twistor in it. And then given the reference twistor, we have propagators that take us from one twistor point to another twistor point, depending on the reference twistor. Okay, and it basically says you get a contribution localized when the 2 points and the reference twistor all lie on a line. So you get something that's localized in this form. There are also interaction vertices, but the only interaction vertices come from those non-local log det terms where I integrated over lines. So all the interactions come from putting in additional lines and gluing propagators to the additional lines. The cubic term in the Chern-Simons form went away because I picked axial gauge. There are no vertices there are no 3 vertices of wiggly lines. Okay, so now we can start computing. So let's do our first computation. We send a propagator across a loop, and after performing the integrations, you can convince yourself the end result is this very simple rational function, which depends on the reference twistor, and only on the sequence of points I minus 1i for one edge, j minus 1j for the other edge. And I think we've seen this in previous talks. This object is called an R invariant, and it comes out to have Grassmann degree 4. Okay, and it should be very familiar from anybody who studied scattering amplitudes. This is the NMHV tree amplitudes are built out of such objects. Simple rational function. Here, ABCD, what does it mean? It means the 4x4 determinant of the formed by the matrix that you get by putting the bosonic, ordinary Z, A, ZB, ZC, ZD, and computing the minor, 4x4 minor. All right, so this gives you in quote-unquote tree-level contribution. We'll call it tree because under the amplitude Wilson loop duality, this would correspond to an NMHV tree amplitude contribution. So we'll continue to call such diagrams trees. And here, there's another type of contribution that I can get by going from edge I to edge J. And this now makes use of the two-fold vertex that I get from the interaction line that I'll call XAB. So if you compute this diagram, you get what's called Kermit, because in somebody's imagination, this looks like Kermit. And it's meant to this diagram is just meant to encode this simple rational function. And you will notice that you obtain things here that also depend on the reference twistor. So I've got 4 poles in the integram that are spurious. They depend on this reference twistor, which was our gauge fixing. And then there are 2 physical poles per diagram that they look like physical poles, or should be familiar also as physical boundaries from the amplitude-hedron picture. Okay, so there's this simple rational function that one obtains. Of course, you have to add up all diagrams. And when you add up all diagrams, you find that the dependence on the reference twistor cancels as it should, okay? Because that was just our gauge choice. So nothing should depend on that. Okay, so this is what you add up. This would be the NMHV tree in amplitude language if I were going across a single loop. But now I can do the same kind of computations for multiple loops. I can send a propagator between 2 loops, and I'll just get a sum of the same objects, same dependence on the reference twistor diagram by diagram. But when I sum over I for one loop, j for the other loop, the dependence on the reference will cancel out. And similarly, I could do the same type of diagram that we had here, where I go via an exchange line with 2 vertices, and I get a sum over the Kermits for line I here and line J here. So this is something new that we didn't have in the first bit of this talk, because it involves the Grassmann variables, and it intrinsically involves the supersymmetric extension that we introduced when we went to twistor space. This is meant to be the same thing as we had before, because this has no Grassmann variables. Okay, each propagator's degree 4 and the integration line's degree -8. So this should contribute to the so-called MHV sector at one loop. Okay, so we should get the same function that we get before, and indeed, you can convince yourself, you sum over all those i's and j's of these rational functions, you can rewrite it in terms of a different rational function, sum of different rational functions, that look like pentagon integrals with some auxiliary extra line x involved. So z star went away, but we introduced this extra line x. Okay, this is following very similar analysis in the paper of Cunningham and collaborators from 2010. You can rewrite the MHV amplitude or the single Wilson loop contribution in terms of the sum of such integrals. Well, you can do exactly the same thing here. Another way of rewriting this is sometimes called a chiral 2-mass easy box integral. We saw such integrals appearing in Jake's talk on Tuesday, I think. Okay, so this is the same language. It's a sum of chiral 2-mass easy boxes. Literally means this thing. You sum these up, and you can actually integrate these. This is a bit hard to integrate directly because it's got all these funny-looking poles. It's not clear how you integrate it term by term. You rearrange the rational function before integration into something that's much more amenable, and you can compute this term by term. It's an explicitly known function in terms of dilogues and logs. Add them all up, and you do indeed get the same function that we had before, when we computed the first contribution in the abelian theory. We sent a single gluon across. That's a good check, right? We haven't wandered out into some fantasy realm. We are getting the same answer that we got from the standard space-time computation. So again, once again, this diagram vanishes in the SUN theory for the same color reason. Okay, so this would be, you can think of this as an abelian contribution. Okay, so for SUN, same trick. You can get it by essentially squaring. So you can get now contributions to the n squared MHV tree, NMHV1 loop, or MHV2 loops. These are the leading contributions that you get for the SUN theory. And they're all given by this perfect square. You square the sum of, you square the abelian result. Right. And in fact, in the abelian theory, if you just study the abelian theory, that's super simple, because then Wilson loops just exponentiate. Okay, essentially, it's a free theory. So you exponentiate this leading contribution, and that's the full answer. And you can organize it into the form that I showed you before. So the Kermits are responsible for giving you the UV divergences and the anomalous conformal finite piece. And then only these extra supersymmetric tree-level parts that you're now exponentiating are the finite remainder of this object in the abelian theory. Okay, and same is true if you can consider multiple loop operators. They exponentiate, and now you have a sum over diagrams, so you get contributions where the Kermit stays in the same loop, and also the R invariant stays in the same loop. You sum over all loops, and you get contributions where the Kermit goes between different loops, R and S, and the R invariant goes between different loops. You add all of those things up, and then you exponentiate, and that's the full answer. So these bits where Kermits stay in the same loop, they're responsible, as before, for all the divergences and the anomalous conformal pieces. And all three of these other terms now contribute to this finite function. Again, to emphasize, this is the full answer, but for the abelian theory. Okay, now there's an interesting differential equation that I mentioned before, which we can now test very easily in the abelian theory because we've got the answer. The differential equation involves this supersymmetry generator. So it's Grassmann d by d bosonic operator, d by dz. This is not a manifest symmetry, but it does have the following property, that if I take an object at degree k, Grassmann degree k, with n external edges, this is now for a single loop, what you should get on the right-hand side is not 0, but it's proportional to the cusp anomalous dimension, which starts at order g squared, so you gain a loop order, times a certain integral over an n plus 1 object at one higher Grassmann degree, with some subtraction, with the same kinematics and degree, but then you integrate it over some collinear limit. Okay, so the derivative of the thing you want is equal to the integral of a thing that's one loop lower. So this equation, so you can, okay, since we're in the, it's convenient to sum over k and package all of this thing in together into all the different sectors of different Grassmann degree. Obviously, if you want a sector of a certain Grassmann degree, you just go to that degree in the Grassmann variable. Okay, now in the abelian theory, although you still have to do something, you have to check that we've got our answer, which was given by the exponentiation of all those R invariants. It does indeed obey the property that if you put this in here, and then you take the collinear limit and you integrate, you get 0 on the right-hand side. And that's good because these R invariants, which are the only things sitting inside R for a single loop in the abelian theory, are all cube R invariant from the get-go. So in the abelian theory, for a single loop, this equation holds, but it's 0 equals 0. It's slightly non-trivial, 0 equals 0. You have to do some work to check it, but it holds because 0 equals 0. Now, if you generalize to multiple loops, we have a very natural generalization. So now I'm going to write the finite part of multiple loop operators. And now the right-hand side should be, you just imagine inserting something on every edge of every loop. And then you integrate over the collinear region that you've introduced. So you have gamma cusp again, sum over all loops, same integral, finite part where you've added 1 point to the rth loop, same subtraction term, and then you cycle over the rth loop. Okay, and now we can take the abelian theory where we've got the answer. And on the left-hand side, this now is a non-trivial function. It doesn't only involve those R invariants, because we had this function that we computed before from space-time, and again from Kermit's, that showed up with dilogues and logs in it. And Q bar is a derivative, so it can't annihilate a non-trivial function. So you're going to get something on the left-hand side. You get Q bar. In particular, what contributes to the left-hand side is the fact that you have G inside the exponent of R, and Q bar G is not 0. In fact, it's equal to this, okay, given by log Q bar log. And now you can convince yourself that if you take the full answer for the finite part for multiple loops, and you do the integration, so here it's the R invariants that contribute to this, you do the integration over the Q bar, over the collinear limit, you do reconstruct these logarithmic terms. So there's actually something to check. Our new function is not 0 on either side, and you can verify that this equation, the natural generalization of the equation, holds for multiple loop operators. This is very good because now you can potentially use this in the SUN theory. Okay, so we checked it in the abelian, showed it in the abelian theory by knowing the answer. And this actually immediately gives us that it has to be true for the leading terms in the SUN theory because they were given to us by the abelian theory. So if we had two loop operators, what did that mean? It means MHV at order G to the fourth. If I do the Q bar, it's the integral over NMHV at order G squared. Okay, I'm continuing to use this MHV, NMHV from the amplitudes language just to count Grassmann degree. So Grassmann degree 0, Grassmann degree 4, Grassmann degree 8. And the same holds between NMHV at order G squared and N squared MHV order G to the 0. The equation holds because it held here. So now we should check in the first non-trivial case that it holds in the SUN theory, beyond this case that followed from the abelian theory. And so we've done a direct computation. We've computed the n-cubed MHV tree amplitude. It's made of diagrams that look like this. And we computed the n-squared MHV one-loop amplitude. It's made of diagrams, for example, that look like this. This thing you can repackage very conveniently using the chiral box basis from Jake's paper with Simon and Yaroslav. Very convenient way to rewrite the integrand that you obtain from this computation. So then you get a bunch of known integrals with some coefficients that you can study, and all of the various types enter in the various different computations. 4 mass, 3 mass, 2 mass hard, 2 mass easy, 1 mass, 0 mass, they're all there, depending on the kinematics. And having computed them and reorganized the answer this way, you have an explicit result here, and we have checked, indeed, that the Q bar of this explicit result, these are all given by dilogues and logs, weight 2 functions, again, explicitly known. The Q bar of this result does indeed follow from the integral over the explicitly computed n-cubed MHV tree amplitude. So therefore, we can declare with confidence that we can make use of this. So in principle, now that we know this one-loop answer, we can integrate it up and compute the Q-bar derivative of the two-loop result. Okay, and this is very analogous to the same kinds of computations that Simon Caron-Hewer and Song He performed and other people subsequently in order to compute higher order in G-squared contributions to these objects without actually doing any diagrammatics or integrand expansion. Okay, so that's to come. And I have minus 10 minutes. No. What do I have? How many minus minutes do I have? -2. Okay. So then I'm just going to show you a picture and finish. So I promised you that I would tell you about BCFW recursion. So there is a way of doing BCFW recursion in the Wilson loop language that rests on this twistorial formulation. I'm not going to go through it. I'm just going to show you what comes out. Here's the end result. You think about shifting one of the points along one of the lines. So you imagine this Zn moves along, okay, and therefore the line that went with it tracks along with it. And so there's some variation of this Wilson loop operator by this parameter that I've called t up here. Okay, as long as I vary t, I vary t in some way, and as I vary t, you should think of this cartoon as a kind of a real version of the complex picture that's happening. Let's think of it in real space. So I now move this line. As I move the line through projected 3 space, it will intersect all the other lines at some point in the deformation. And when it does, you get a diagram that looks like this, where 2 lines intersect from the geometry. Okay, and then there's an argument based on this Wilson loop formulation and the loop equations of Makienko-Migdal that you can write. You get contributions to the variation that are localized at such points when these things intersect. You get a sum over contributions from intersecting configurations. So that gives you something that looks vaguely like this. You have to integrate, well, it's really a sum because it gets localized by some delta function, to a correlation function of 2 loops that are the left half and the right half in this intersecting configuration. Okay, and the correlation function is something that we've just been computing. In the large n limit, however, you can take this large n limit, and we saw that the leading term, these things factorize. So this thing factors into a left half and a right half. Okay, and this is now, morally, this is the BCFW recursion relation, right? So the thing you started with, okay, so there's a boundary term where it's got 1 point removed, and then it's a sum over contributions that factor into left and right halves, just like the BCFW recursion relation. So you can apply literally the same logic. So let me skip this and just go to this. So sometimes people write it in this, draw pictures like this. So I've been learning this from Matteo, in Matteo's papers with Lauren and Ran and company. They draw diagrams like this that illustrate the BCFW recursion relation. And this is just meant to be, you solve some linear algebra problem to work out effectively what the intersection points in the geometry are. And then you put in a left piece and a right piece. And then this orange bit in the middle is some R invariant factor that comes up front. So you can do literally the same logic for a correlator, connected part of a correlator of multiple loops. You get a more complicated looking equation. You can move one of the lines on one of the loops and it can self-intersect. And then you get a bunch of terms that correspond to that, directly analogous to the recursion we just saw. But you can also get that it now intersects the lines from the other loops. And you get a new type of term where you get a big Wilson loop that goes around everybody. So I'm not going to go through that, but I'll show you the cartoon version of this picture corresponding to the same linear algebra problem in the pictures that the analog of the pictures from Matteo's paper. So this is the first type of term, very directly analogous. We've now got 2 boundaries, the black with 2 sets of data, they're the 2 Wilson loops, and then you get the BCFW bridge, which is the R invariant, and then the blue objects are on this side a Wilson loop, and on this side a correlator of Wilson loops with this external data and this internal data. And the new type of term looks like something like this. You get the BCFW bridge between the 2 boundaries, and then you're meant to glue everything, all the data, into a single big Wilson loop that goes all the way around. And this corresponds to this new type of term. Okay, so I am more than minus 10, so I'm going to stop.